balancing equations. Let's get started. So first question is, why on earth do we even bother balancing equations? Well, it has to do with the law of conservation of mass. Now, I've put the definition over here. You can have a look on the internet or look in your notes. Um, we did do this experiment in class, which demonstrates the conservation of mass. It's the idea that the mass at the beginning of a reaction is going to be the same as the mass at the end, so long as you collect all the products. And part of the difficulty with collecting all the products is that sometimes those products come in gas form. So when we did the experiment where we put the balloon on top of the Erlenmeyer flask and collected the carbon dioxide that was coming off, if we hadn't put the balloon there, we would have lost that carbon dioxide and it would have looked like we had lost mass in the experiment, when in actual fact, we just didn't collect all the products. So reactions do not lose mass. They may change form. They may go from a solid form to a liquid form to a gas form. They may change states. However, they do not disappear. They're not destroyed. So when we write out a chemical equation, we have to keep that in mind. We have to think that the ratios of all of those elements are actually going to determine the mass of the entire reaction. And it's really important that we do that when we write out a reaction. So let's have a look. The very first thing we need to check out is that when you balance a reaction, you have to do a good job of writing out the skeleton equation. That requires, if you're given a word equation, that you write out the skeleton equation by balancing the charge. If you can't remember how to do that, go back and look at the nomenclature video and have a check over to see if you can do it. So what we're going to do here is we're going to write out the chemical formula. So I'm just going to at first write out all of the chemical symbols for all of these. And then we'll have a look at the periodic table to determine their charges. And then we'll write out our skeleton equation. So we have potassium and chlorine, calcium, and iodine. Now, we need to go and have a look at our periodic table and find out what the charges are of these. So calcium, if I look at my periodic table, it has a charge of 2, and potassium a charge of 1. Let's go back and put those charges in. So calcium had a charge of 2. Sorry, my pen's reacting a little funny here. 2 plus. Calcium had a charge of, or potassium, sorry, had a charge of 1 plus. So let's put those all in. Okay, now let's look at our nonmetal components. We have chlorine and iodine. And chlorine and iodine are in the 7th column, which means they both have a charge of -1. So let's go put those back in. Okay, now we can balance the charge and create our chemical equation. So 2 here, +2 and -1 means that I need 2 chlorine for every 1 calcium. So when I write out the compound, it's going to look like this. Calcium chloride with 2, okay? Then we have, I'm going to bring down this plus sign. Then we have potassium and iodine. Now they're +1 and -1, which means I don't need to do anything. They balance each other quite nicely for charge. And we'll move on to the product side. We have potassium and chlorine. They both have a charge of 1, so we don't have to do any changes. And then we have calcium and iodine, which is going to give us a change here because calcium has 2, iodine 1, which means I need 2 iodine for every calcium. Now that we have everything balanced nicely, we can now start balancing the number of atoms from product side to reactant side. That is our goal of balancing an equation. What we need to do is make sure we have the same number of chlorines, or calciums, chlorines, potassiums, and iodines from the product side to the reactant side. You can use a table to do this if you'd like. For some people, that visual representation is really helpful. So you could do it out like a table like this and start here, 1 and 1. Or you can do it another way, which is the way we've kind of been working on in class, which is here is my skeleton equation, and I'm just going to go from side to side and count. So I have 1 calcium here and 1 calcium here. Yay, we're balanced. 1 atom, 1 atom. 2 chlorine on the reactant side here, and only 1 chlorine on the product side here. Now, can I use a subscript to balance this out? No, do not use subscripts. Subscripts are only for balancing charge. So what do we use? Here, we're going back to our math vocabulary. We're going to use coefficients. Now, coefficients are the numbers that go in front of the numbers, really large, okay? And the way they work is they are distributed through, just like in math. So if I was to look at a math equation that had a number out front as a coefficient, let's say I'm doing 3 times x plus y, okay? This number is going to get distributed all the way through the brackets. Now, that's going to end up looking like this, okay, in math. No different in chemistry. When you put a coefficient out in front here, as we're going to do in the case of calcium, we need a 2, so we're going to put a 2 here. That 2 is then distributed to the potassium and to the chlorine, which means I have 2 potassium and 2 chlorine. Okay, so that coefficient essentially multiplies through the compound. When does it stop? If you come to a mathematical symbol, a plus sign or an arrow to indicate reaction, that's when it stops multiplying through. Okay, so now we have fixed up the chlorines. We have 2 here and 2 here. Let's move on. We have 1 potassium here, and because we added a 2 in front of here to fix up the chlorine, we've actually made it so that there are 2 potassium on this side. Now, because there are 2 here, we need to balance it out atom for atom. We need to go back to the reactant side and make this equal 2 as well, which means I'm going to put another coefficient in front, 2, which is going to satisfy 2 potassium, 2 potassium. What I've done now is change the amount of iodine. So I now have 2 iodine here, but look, this subscript means I have 2 iodine already here. This is a balanced equation. Okay, I have the ratios of atom for atom the same from reactant side to product side. Let's make it a little more tricky. Okay, so we have a skeleton equation here. It has some polyatomics in it. Polyatomics, again, remember their charge applies to the entire polyatomic, so when you balance it out to make that really nice, neutral, balanced charge skeleton equation, you have to use for all of the polyatomic. So we have potassium phosphate, calcium sulfate, reacting to create potassium sulfate and calcium phosphate. What we need to do is balance it from side to side. Now, some tips and tricks. Try balancing the polyatomics first. If they exist on the reactant side, like this phosphate here, and they're on the product side, you can actually balance them as if they are the entire ion. You don't have to go P for phosphate, oxygen, oxygen. You can balance the entire phosphate. So let's do those first. You want to do those first. So we have 1 phosphate here and 2 phosphates here, which means we have to change this to balance itself out with the 2 over there. So we're going to put a 2 in front here as a coefficient. That's going to give me 2 phosphates, and I have 2 phosphates here. Let's look at the other polyatomic, 1 sulfate, 1 sulfate. That part's good. Now we can move on to the other elements in this particular equation. So here I have 2 times 3. Now, so this is the multiplication part. 2 coefficient times 3 subscript potassium gives me a total of 6 potassium. Over here, I only have 2 potassium. So what subscript do I need to put in front in order for that to work? Well, I'm missing a 3 here. If I put a 3 here, as a coefficient. That gives me 3 times 2, 6 potassium, 6 potassium. What I have also done, however, is I've changed the number of sulfates. So here I now have 3 sulfates. Here I only have 1, which means we're going to put a 3 here in order to fix that up. So 3 here. Okay, that gives me 3 sulfates, 3 sulfates. It also gives me 3 calcium, which is good because over here I have this little subscript telling me I have 3 calcium. This makes a very balanced equation. This is the balanced equation for that reaction. Now, the second hint is that you try and leave hydrogen and oxygen till the end. Now, why do I do that? Because oftentimes you'll find that in reactions, oxygen and hydrogen can be found in 2 places, even just on the reactants or the product side. So if we have a look at this equation, this is cellular respiration, by the way, if you're headed into biology. We have glucose and oxygen combining to make carbon dioxide and water. So here we have oxygen in this glucose molecule, but we also have oxygen by itself. If I was to try and balance those first, it's going to change rapidly. So it's easier to balance the other things first. So I'm going to start with the carbons. I have 6 here and 1 here. So I'm going to need to change that. I'm going to put a coefficient in front of 6. That now gives me 6 carbon and 6 carbon. Okay. Because I have oxygen in 2 places here, I'm going to leave it until the end. I'm going to try and do the hydrogens first. I have 12 hydrogen here and 2 here. In order to make this equal 12, I'm going to put a 6 in front here. That's going to give me 12 hydrogen. I now have 12 hydrogen here, 12 hydrogen here. What have I done? Well, here, look, we've changed the number of oxygen on the product side drastically. We now have 12 oxygen here and 6 oxygen here. We have to combine them together. That is a total of 18 oxygen. Okay? So 18 oxygen on this side means I have to have 18 here. I already have 6 here, so I can actually do a tiny little bit of math, as much as I can go 18 subtract 6, which actually gives me 12. And because I have 2 here, I only need to put what's going to give me 12 out of this 2. So I'm actually going to put a 6 here, and that gives me 12 here. So I now have 6 and 12, which is a total of 18, and 18 oxygen here. This is a balanced equation. So some tips and tricks for balancing equations. Try balancing the polyatomics first if they both exist from reactant side to product side. Try and save hydrogen and oxygen until the end because oftentimes you'll find them in more than one compound, even on a reactant side, or more than one compound on a product side, and that will change the numbers drastically. This is a back and forth thing. This is something you're probably going to have to erase coefficients and change as you go. There's nothing wrong with that. That's just the way this works. I can't give you a quick silver bullet solution, but if you do a little practice, you should be able to get it. Happy balancing.